Hi, my name is Michael Kaler, and I am the manager of the Diffraction Facility housed in the Joint Institute for Advanced Materials. JIAM is a joint venture of the University of Tennessee, Knoxville and Oak Ridge National Labs. In this video, I will introduce you briefly to the theory behind how diffraction patterns are generated, and then go into the types of measurements we can make at the diffraction facility and take a look at what the data can tell us. If there are X-ray diffraction techniques that are not covered here that you would like to perform at the diffraction facility, please email me. Both my email address and a link to the diffraction facility website are in the description of this video. I would also like to caution that the information presented here is very shallow. Often there is more to the theory, analysis, or calculation than I am telling you. The purpose of this video is to introduce some of these concepts to you in an easily understandable way and get you thinking about how X-ray diffraction can help your research. Now let's get started with the very basics. Whether gas, liquid, or solid, atoms make up all things. How those atoms behave determines what state of matter is present. In gases, atoms are spaced far apart and move rapidly. The atoms in a liquid behave somewhat similarly to those in a gas, but they are closer together and move more slowly. Finally, atoms are relatively stationary in the case of solids, and while rapidly cooling liquids can produce solids that have atomic structures similar to liquids, in other words, largely disordered with some short-range order, the majority of solids have long-range atomic order. In the example presented here, the atoms form a simple cubic structure. This structure, called a unit cell, is the basic building block of the material's symmetry. These unit cells have neighbors that are aligned the same. The example shown here utilizes a mere 4 unit cells. Now, crystallographic planes of atoms are crucial to X-ray diffraction. If we highlight this plane of atoms, choose these as our reference axes, and choose this as our origin, then the highlighted plane would be the 1, 0, 0. We designate planes by finding the number of atomic spaces that the plane crosses each axis, and then take the reciprocal of each number. For instance, the 1, 0, 0 plane crosses the x-axis at 1 atomic spacing, and the y and z axes at, theoretically, infinity. The reciprocal of 1 is 1, and the reciprocal of infinity is 0, hence 1, 0, 0. If we were to now highlight this new plane of atoms and shift our origin back to this position, we can see that this plane can also be described as a 1, 0, 0. There are also other types of planes in this simple cube. If we highlight the planes that cut through the unit cells as shown here, these new planes are 1, 1, 0 planes because they cross the x and y axes at 1 atomic spacing and the z-axis at infinity. Taking a top-down perspective, we can see that the distance between two equivalent planes, also called a d-spacing, is dependent upon the type of plane. Now let's focus on the 1, 0, 0 planes. In X-ray diffraction, we have a source of X-rays and a detector. The source shoots X-rays at the sample, then the X-rays are diffracted by the sample and picked up at the detector. The X-rays have a certain wavelength. The angles at which the X-rays strike the sample and are diffracted are designated by theta in the so-called powder diffraction configuration. If the X-rays from the top path reach the detector at the same point along the wavelength as the X-rays from the bottom path, constructive interference occurs and a peak is produced when the intensity is plotted as a function of 2 theta. If the X-rays reach the detector at different points along the wavelength, destructive interference occurs and all we get is background. In order for the bottom path of X-rays to reach the detector at the same point along the wavelength as the top path, the bottom path must travel some additional integer multiple of wavelengths compared to the top path. In the example shown here, the 2 extra wavelengths that the bottom path travels are shown in red. If we apply some basic geometry, we can determine how the wavelength, d-spacing, and theta are related. Making use of the sine function, the wavelength can be shown to equal the d-spacing times the sine of theta. This only takes care of half of the additional length that the X-rays must travel. Because there is another half, the total additional distance that must be traveled by the lower path is 2 times the d-spacing times the sine of theta, which gives us Bragg's law, the law that outlines the condition that must be met in order to obtain constructive interference and a diffraction peak. Shown here is the same d-spacing and wavelength, but the angle theta has now been increased. It is clear the X-rays no longer constructively interfere since the bottom path is no longer traveling an additional integer number of wavelengths. At this angle of 2 theta, no peak will be produced by the 1, 0, 0 plane. Now I'll switch to showing the types of measurements that can be accomplished in the JIAM Diffraction Facility. When most users come to the facility, the first thing they want to do is identify the phase of their material. Whether you synthesized the material yourself or received it from someone else, it is vitally important to make sure that the material is what you believe it to be. For example, here is a tungsten disulfide powder, and here is a silicon oxide and manganese oxide mixture that I made for a later portion of this video. Often we can't tell what a material is simply by looking at it. Fortunately, X-ray diffraction can show the differences that our eyes alone can't detect. A useful aspect of diffraction is that each material has its own diffraction pattern. The example shown here is for silicon, and each peak corresponds to a particular atomic plane as indicated. After collecting a diffraction pattern for your material, you can compare it to the PDF4 Plus database, which contains over 380,000 other patterns to find a match. Access to the PDF4 Plus database is available in the diffraction facility. This diffraction pattern can also be used to determine the size of the unit cell. If we take Bragg's law and recognize that the wavelength remains constant throughout the experiment and n can be ignored for the purposes of calculation, our remaining variables are the despacing and the angle. We can get the angles at which Bragg's law is obeyed by determining the peak locations in the diffraction pattern. We can then solve Bragg's law for the despacing of each plane for which we have a diffraction peak, which allows for the calculation of the lattice parameters. In the simple cubic example from earlier, the despacing of the 100 plane gives all three lattice parameters A, B, and C. For the example shown on the left of the screen, it took less than 2 minutes to load the data into the analysis software and obtain the lattice parameters with incredible accuracy. Granted, this is an ideal reference material, so your experience may not be as fast, but the process is quite straightforward. If your material is a solid solution, utilizing Viguard's law along with the lattice parameters of the pure constituents and your sample could help you determine the composition of your sample. The previous slide covered the case in which the material was a single phase. Many times, however, users come to the lab with samples composed of multiple phases. Shown here is the diffraction pattern for the sample containing both silicon oxide and manganese oxide that I showed you earlier. If you look at the unit cells on the right of the screen, you can see that the shapes are very different. Because of this, each phase has a distinct diffraction pattern. The blue lines in the diffraction pattern designate the silicon oxide peaks, while the green lines designate the manganese oxide peaks. The software available in the diffraction facility greatly helps in the determination of which peaks belong to which phase. If the sample is prepared and tested appropriately, you may also be able to determine how much of each phase is in your material. When making the sample, I had weighed 50.4% silicon oxide and 49.6% manganese oxide. As you can see, the analysis is very close. Phase quantification utilizes peak intensities. We are able to obtain information from the breadth of the reflection too. For instance, if we have crystallite sizes of 100 nanometers, the full width half maximum, or FWHM, of the reflection should be around 0.1 degrees. If the crystallite size is reduced to 5 nanometers, the full width half maximum should be around 1.75 degrees. Typically, we like samples with a crystallite size of a few microns. However, we can certainly accommodate crystallite sizes on the nanometer scale as long as you don't mind the peaks looking very broad. In order to calculate the crystallite size, a popular method is to utilize Scherer's equation, shown here. It is a pretty straightforward equation where the crystallite size equals the shape factor, typically taken to be around 0.9, times the wavelength of the X-rays divided by the product of the full width half maximum in radians of a particular peak and the cosine of the Bragg angle of the same peak. This equation appears so simple, but you can't let the simplicity tempt you to use it with less consideration than you should. For instance, based off of what I have told you so far, you would think that the sample that produced the black curve should have a much smaller crystallite size than the sample that produced the blue curve. Surprisingly, both patterns were made with the same sample. The difference is that different diffractometers and optics were used. This illustrates the fact that there is some inherent instrumental broadening of the data you collect related to the incident and diffracted beam optics that must be accounted for before further analysis. Another issue is that in addition to instrumental broadening and broadening due to crystallite size, microstrain also affects the breadth of your peaks. For instance, imagine that you have a crystal lattice with an extra half plane of atoms. The despacings for the atomic planes around this extra half plane of atoms now varies instead of being the same. If we were to take these despacings and apply them to the diffraction pattern, we can see why microstrain broadens the peak. Recall that every despacing corresponds to a particular value of 2 theta that brings about a peak. If the d-spacing of a particular plane now has a variety of values larger and smaller than the average, this means that the angles larger and smaller than the Bragg angle will also bring about some sort of intensity, thereby broadening the peak. Fortunately, there is an equation that also governs the effects of microstrain. The broadening is equal to 4 times the strain times the sine of theta divided by the cosine of theta. If we combine this with a broadening due to the crystallite size, we can make a Williamson-Hull plot. If we plot it so that the y-axis is the full width half maximum after having corrected for the instrumental broadening, times the cosine of theta, and put the sine of theta on the x-axis, then fit the data with a straight line, the y-intercept gives the crystallite size and the slope gives the microstrain. For this sample, it was determined that the crystallite size is approximately 100 angstroms and the microstrain 0.12%. Another function of XRD is the determination of the degree of crystallinity. Crystallinity refers to the amount of order in your material and can have a large influence on material properties. Gases have atoms that are completely random, which means no crystallinity. Amorphous materials have limited short-range order on the scale of a few atomic or molecular distances. Crystalline materials have a long-range order of at least tens or hundreds of atomic distances. There are some materials, such as polymers, organics, and ion-irradiated materials, that have a mixture of amorphous and crystalline regions. To this point, we have looked only at crystalline materials. The images shown here, however, correspond to semi-crystalline materials. The diffraction patterns of semi-crystalline materials have sharp crystalline peaks along with broad amorphous peaks. Determining the degree of crystallinity of such a semi-crystalline material requires first deconvoluting the diffraction pattern. For instance, an example of the raw data is shown in the figure. This pattern is a sum of all peaks. Utilizing software such as HiScore Plus or Origin, we are able to determine the contribution from each peak. Such analysis should also give the area beneath each peak, which can then be used to calculate the degree of crystallinity by dividing the total area of the crystalline peaks by the total area beneath all peaks. The only difference between this next technique and the ones we have covered so far is that we are able to perform the diffraction experiments at non-ambient temperatures and environments. Our Empyrean diffractometer ranges from room temperature to 1200 degrees Celsius in air, vacuum, or inert gas environments, while our Huber diffractometer ranges from 10 Kelvin to room temperature in a vacuum environment. Today, I'll show you 2 types of high-temperature experiments performed in the JIAM Diffraction Facility. The first is an equilibrium experiment investigating a sample's phase transformation, and the second type is a kinetic experiment of the synthesis of a compound from starting materials. As the compound for the first example has a rather complex pattern, this figure shows only a small region for clarity. In this experiment, the temperature was increased to a desired value, and the sample was allowed to reach equilibrium before the data were collected. The first item to note is that we see a new peak appear just below 40 degrees 2 theta in the pattern collected at 300 degrees Celsius. Using the full diffraction pattern, the user was able to determine the identity of this phase. More experiments could be carried out to better determine at which temperature it first appears. Looking at the peaks around 38.7 degrees 2 theta, we can see that as the temperature increases, the position of the peak shifts to lower 2 theta, indicating an expansion of the lattice parameters. From these data, we can determine the values of the lattice parameters as a function of temperature and therefore determine the thermal expansion. This example of a similar experiment on a zirconium oxide sample shows the power of X-ray diffraction in the determination of anisotropic thermal expansion, or thermal expansion that is different for different directions. We can see that the peaks for the 002 and 200 planes shift to lower angles with increasing temperature, while the 020 peak remains relatively unchanged. In a single series of experiments, values for each lattice parameter can be determined for each temperature. The next high-temperature example has a plot that looks vastly different than the last one. For this kinetic experiment, the data were collected while the temperature was increased to 1200 degrees Celsius. Never did the user allow the system to pause at a temperature to reach equilibrium. Each of the vertical lines that you see in this plot corresponds to a peak in the typical intensity versus 2 theta type of plot. The color of each line indicates the intensity of the peak. In this experiment, the user began by mixing 2 materials, aluminum oxide and calcium carbonate, and pressing them into a pellet. That pellet was then placed in our system and data collection began. Once the temperature reached approximately 700 degrees Celsius, the calcium carbonate transformed to calcium oxide and CO2 gas, while the aluminum oxide did not react. If you look above and below the red line on the figure, you'll see some peaks continued from the lower region to the higher region. These are from the aluminum oxide. Some peaks ended. These are from the calcium carbonate. Finally, some new peaks appeared. These are from the calcium oxide. As the temperature continued to rise, the user saw another transition around 850 degrees Celsius. This time, the aluminum oxide did react with calcium oxide to form both compounds shown here. With this one experiment, the user was able to determine the reactions and reaction temperatures for every step of the material synthesis. If your sample is a thin film on a substrate or an ion-irradiated material, conventional Bragg-Brentano XRD may probe too deeply beneath the surface for you to study the region of your material that is interesting. As shown in the left panel, the X-rays interact with the substrate much more than the thin film, which is reflected in the diffraction pattern as a weak contribution from the thin film and a strong contribution from the substrate. With knowledge of the expected composition and density of your material, however, we can estimate the penetration depth of the X-rays as a function of omega, which is the angle at which the X-rays strike your sample. This helps to ensure that you only study the depth of your sample that is most interesting to you. As shown in the right panel, we can then hold the incident angle constant while the detector rotates through 2 theta, thereby keeping the penetration depth constant throughout the experiment. This is called grazing incidence X-ray diffraction. Our users regularly utilize this technique for phase identification, lattice parameter calculation, and the determination of the crystallinity of their samples. In a moment, I'll show you a real example of data collection from 40 to 50 degrees 2 theta using both Bragg-Brentano and grazing incidence configurations. But first, I'd like to point out some of the different parts of the diffractometer. On the left is the X-ray source, and on the right is the detector. In the center is the sample. All of the other stuff in the X-ray path is used to condition the beam. We can use different configurations to control the size of the X-ray footprint on the sample, how spread out the beam is, etc. Here you see the system in the Bragg-Brentano configuration, so the source and detector both begin at 20 degrees, which makes a starting 2 theta angle of 40 degrees. They then rotate at the same rate upward by 5 degrees, which makes an end angle of 50 degrees. This results in a very weak peak. Now we go to the grazing incidence configuration. The source moves to an angle of 4 degrees, while the detector moves to 36 degrees. The detector then moves upward by 10 degrees, and we see that the peak is larger. We now remain in the grazing incidence configuration, but the grazing angle is reduced to 1 degree, and the detector moves to 39 degrees. Again, the detector rotates by 10 degrees to bring the total end angle to 50 degrees, and we see the peak intensity has continued to increase. Finally, the grazing angle is reduced to half a degree, and as you'll see in a moment, the peak intensity increases further. Now, in case I'm leading you to believe that the peak will continue to get larger as you decrease the angle, there is some angle at which the X-rays no longer penetrate into the material and you stop seeing peaks altogether. Another technique that is beneficial for thin films is X-ray reflectivity, or XRR for short. XRR utilizes the Bragg-Brentano geometry where the source and detector both rotate, but the angles are kept smaller than for standard powder diffraction. In the example here, omega did not get above 3 degrees, which means that 2 theta did not get above 6 degrees. A not-to-scale diagram of the type of sample that can be studied with this technique is shown on the right. The sample can have one film or multiple films on a substrate, but the roughness values must be less than about 2 nanometers, and the film thickness must be less than about 1,000 nanometers. While explaining the physics behind XRR is outside the scope of this video, I will say that the oscillations that you see are due to the interference of the X-rays reflected from the surface and the X-rays reflected from each of the interfaces. Because of this, the oscillations give us information regarding the thickness of each film, the roughness of each interface, and the density of the films and substrate. Using software available in the diffraction facility, you can determine values for each of these sample properties. The next technique works with solid pieces of material and thin films. However, to really understand what pole figures can tell you, we need to take a step back and look at the conditions for diffraction again. The diagram shown here is a more realistic representation of diffraction. For polycrystalline samples, there are small regions called grains in which all unit cells are aligned in the same way. These grains are outlined in red in the figure, and neighboring grains have unit cells that are oriented differently. Let's pretend that the lines within the grains shown here correspond to the 100 plane, and that the X-ray source and detector are at the proper angles for constructive interference to occur for the 100 planes, normally producing a peak in the diffraction pattern. The diffraction vector shown here is the vector that bisects the angle between the X-ray source and detector. In this example, the diffraction vector points straight up and is perpendicular to the diffraction plane. Here are the normals for the 100 planes for each grain. The only grains that will contribute to the appearance of the diffraction peak are those whose normals align with the diffraction vector. In other words, this grain is the only grain shown here that will contribute to the diffraction peak. Now let's look at a sample with preferred orientation. In this example, our diffraction vector is the same as before, but the 100 plane normals are different. For this sample, there is a clear preference for the 100 normals to point up and to the left. Because none of the normals are aligned with the diffraction vector, no grains will contribute to the diffraction peak, so only background will be visible for this atomic plane, even though the source and detector are at angles that should produce a diffraction peak. When we collect pole figures, we align the source and detector at angles such that diffraction from a certain plane should occur. We then rotate the sample around two axes to determine qualitatively how many grains are aligned with the diffraction vector at each position. Let's go ahead and look at a real-life example. On the right, we see the setup for collecting pole figures. Here is our sample, a square piece of cold-rolled copper. X-rays strike the sample from this direction and diffract off in this direction to be picked up by the detector off-screen. The system has been set up so that the source and detector are positioned such that the 111 reflection should be detected. Once the measurement begins, the first thing that will happen is that the sample will rotate 360 degrees in phi, which will be represented as the appearance of data in a similar fashion on the left. The sample will then rotate back into the screen in chi, which will be represented as a movement away from the origin in the pole figure. As I said, we first rotate along phi and we see almost no intensity on the plot, indicating that there aren't any 111 planes oriented correctly for diffraction. We then rotated a bit back in chi, then rotated in phi again while collecting data. This time we start to see some intensity appear, so some 111 planes are oriented correctly. As we continue to rotate further in chi, more intensity is seen at certain parts of the plot. We continue this until chi reaches approximately 70 to 80 degrees, because it is at this point that the X-ray beam typically begins to fall off of the sample. Because this type of experiment deals strictly with the intensity of the peak, the entire X-ray beam must remain on the sample throughout the experiment. We see that at certain orientations the intensity is much stronger. This tells us how the 111 planes are preferentially oriented in our sample. We are not limited to only investigating one type of plane. If we were to rotate the source and detector to the angles that should produce other planes, we can do the same experiment and determine each plane's preferred orientation. For this cold-rolled copper example, I also tested the 200 and 220 planes. Depending upon your material, you could get very different looking pole figures. Here are some pole figures for an epitaxial thin film. An epitaxial thin film is either a perfect or nearly perfect single crystal, meaning that the entire sample is made up of a single grain and all unit cells are oriented the same. Because of this, each type of plane only diffracts constructively at very discrete orientations. We have now reached the final technique that will be covered in this video. Recall that in the case of a single crystal, material properties such as elasticity, strength, hardness, and others can all be dependent upon which atomic plane the testing force is applied. Because of this, researchers need to know how the atomic planes are oriented within the sample. In order to accomplish this, Laue can be performed. In a Laue experiment, we have an X-ray source, some sort of film, and the sample. Just to clarify, the sample does not need to be any particular shape. I just used a cube as an example. The X-rays are shot through the center of the film, strike the sample, and are reflected back to the film, producing a pattern like this. Each one of these dots corresponds to a diffraction peak for a particular atomic plane. Utilizing software in the lab, we can determine which planes the dots belong to. The dot that I made green belongs to the 100 plane, which is the plane on which I wanted to test. The software not only identifies the planes, but it can also tell you how to rotate the sample in 3D space to make it perpendicular to the X-ray beam. Using our goniometers, I rotated the sample, ran another test, and found that the 100 plane was now in the center of the pattern, which means that it is perpendicular to the X-ray beam. I then cut the sample so that the new face would correspond to the 100 plane. Additional experiments could be performed to cut more faces to correspond to whichever planes are desired. That brings us to the end of the video. If you would like more information about the JIAM Diffraction Facility or have any questions, here is the address for our website and my email address. Thank you for watching.